All right, in this video, we're going to talk about section 4.1, which is maxima and minima. We're going to begin a new chapter, which is chapter 4, dealing with the applications of derivatives. So far, we've already talked about basic mechanics of derivatives and evaluating them and interpreting them as rates of change. So now we're going to apply derivatives to a variety of mathematical questions about properties of functions and their graphs. One outcome of this work is a set of analytical curve sketching methods that produce accurate graphs of functions. Equally important, derivatives allow us to formulate and solve a wealth of practical problems, like a weather probe dropped from an airplane accelerates until it reaches its terminal velocity. And we wanted to know when is the acceleration the greatest. Okay, and an economist has a mathematical model that relates the demand for a product to its price, and what price will maximize the revenue. So in chapter 4, we're going to develop tools needed to answer such questions. In addition, we'll begin an ongoing discussion about approximating functions. We're going to present an important result called the mean value theorem, and we will work with a powerful method that enables us to evaluate a new kind of limit. So in this chapter, we're going to conclude with two important topics: a numerical approach to approximating roots of functions, which is called Newton's method, and then we'll end it with a preview of integral calculus, which is going to be the subject of chapter 5. But for now, in section 4.1 in this video, we're going to look at maxima and minima. Okay, with a working understanding of derivatives, we now undertake one of the fundamental tasks of calculus, analyzing behavior and producing accurate graphs of functions. An important question associated with any function concerns its maxima and minimum values. On a given interval, perhaps it could be the entire domain. Where does the function assume its largest and smallest values? Questions about maximum and minimum values take on added significance when the function represents a practical quantity, such as the profits of a company, the surface area of a container, or the speed of a space vehicle. Okay. Now we're going to begin with the definition of absolute maximum and absolute minimum. So here's the definition here. It says here we're going to let f be defined on an interval containing c, and that interval is going to be I. If we have f of x, f of c being greater than or equal to f of x for every x in the interval I, then that means that f has an absolute maximum value of f of c on that interval I at c. And also, if f of c is less than or equal to f of x for every x in the interval called I, then that means that f has an absolute minimum value of f of c on that interval I at c. Now, sometimes they refer to absolute maximum and absolute minimum values as global maximum and minimum values. Okay. Now, from that, we have Theorem 4.1 dealing with the extreme value theorem. And that states a function that's continuous on a closed interval AB has an absolute maximum value and an absolute minimum value on that interval. All right, so in these next two examples I'm going to show you on the next page, we're going to be identifying absolute extreme values on a closed interval AB. Okay, so in this case here, let's say we want to determine from the given graph whether the function has any absolute extreme values on the closed interval AB. Okay, so here's a graph right here, and I'm going to use brackets at A and at B, because that's the closed interval. Okay. And I want to identify the absolute maximum and the absolute minimum. And of course, absolute minimum. All right, in this case here, your absolute maximum, that's going to be the highest point for this graph on the interval AB. And that's going to be this point right here. And that highest point occurs at x is equal to B. So the absolute maximum would be at x is equal to B. And then our absolute minimum, well, that's going to be the lowest point right here. So here, this will have to be the lowest point here. That's as low as it will get before it starts increasing. And that lowest point occurs at x is equal to C2. So at x is equal to C2, we have an absolute minimum. Okay. All right, now example 2. Again, we're going to determine from the graph whether the function has any absolute extreme values on the closed interval AB. So this is our closed interval from A to B. And I want to know what the absolute maximum is and the absolute minimum, if there is one. Because sometimes there is no absolute maximum and or no absolute minimum. So here's the graph. Now, you would think the highest point would be up here, but unfortunately, there's an empty circle there, okay? Now, we can't say that this will be the absolute maximum because there are infinitely many points that get closer and closer to this point, but they'll never reach that point. So in this case, there is no absolute maximum. So we're just going to say none. And then for the absolute minimum, you would think this will be the lowest point. However, it also has an empty circle there. So this has no absolute minimum. Okay. So that's how we identify absolute maximum and absolute minimum. All right, now let's look at local maxima and minima. And here's its definition. Suppose C is an interior point of some interval I on which f is defined. If f of C is greater than or equal to f of x for all the x in I, then f of C is a local maximum value of f. And if f of C is less than or equal to f of x for all x in the interval I, then f of C is a local minimum value of f. Okay. Now here they use relative maximum and relative minimum as another way of saying local maximum and local minimum. Okay. Now, you've probably seen this before in a college algebra class when we talk about relative maximum and relative minimum. Let's say we had a graph that looks like this. Well, I'm just drawing the vertical and the horizontal axes. Let's say my graph looked like this. This represents the graph of y is equal to f of x. And as you can see here, let's say on the interval A to B. And it's going to be a closed interval, so we'll use brackets at A and at B. So the highest point here, that would be that highest point, would be your relative maximum. And also the lowest point right here, that's this point here, that's the lowest point it will ever get before it starts increasing. That would be called the relative minimum. Okay, the relative minimum. All right. So if we look at example 3, here we're going to use the graph to identify the points on the interval AB at which local and absolute extreme values occur. So in this case, here we're going to be identifying the local minimum and local maximum. So with the local minimum from A to B, that's this interval here, from A to B, this will be a minimum point right here, and it occurs at point at x equals q. So at q, that's a local minimum. Now for a local maximum, there's a couple of points here that reaches up and then starts going down. And then we have another one that goes up, reaches this point, and goes down. That happens at both P and R. So at P and at R, we have a local maximum. And of course, that local minimum, which is Q, that means in this case, it's going down to this point and then it goes back up. Okay, that would be considered the local local minimum. All right, now point B would not be a local maximum because it just stops at this point right here and it's not going back up. Okay, maybe that would pretty much explain that a little bit better. Now for the absolute maximum and minimum. Well, let's start with the absolute minimum. The absolute minimum would be the absolute lowest point on the interval A to B. And in this case, that would be this point right here, and it occurs at x is equal to B. And now for the absolute maximum. Absolute maximum, that's the absolute highest point from A to B, and that occurs right here at x is equal to P. So at P, that's our absolute maximum. Okay. All right, now next we'll talk about critical points. Critical points. And here's theorem for that 4.2. And it states if f has a local minimum or maximum at C and f prime of C exists, then f prime of C has to be equal to 0. Okay, that's pretty much how we find the local extreme point or the critical point. Okay. Now it says here that local extrema can also occur at point C where f prime of C does not exist. And in the figure that I'm going to show you, which is what you see here on the screen, it shows two cases. One in which C is a point of discontinuity, and the other one in which F has a corner at point C. Here's the one on the left where there is a hole in the graph at y equal f of x. So here we have a point of discontinuity there. So here, f prime of C does not exist. Okay, so here we have a local minimum at C. Now the one on the right has a sharp corner in the graph, and that sharp corner occurs at x is equal to C. So here you could have a local maximum at C where f prime of C does not exist. Okay. All right, now on the next page, here's the definition of a critical point. Okay, because local extrema may occur at point C where f prime of C equal to 0 and where f prime of C does not exist, here we have our definition of a critical point. An interior point C of the domain of f at which f prime of C is equal to 0 or f prime of C fails to exist is called a critical point of f. So when we find out critical points, all you're going to do there is take the first derivative of that function and set it equal to 0 and simplify. And those x values will tell you what your critical points are. Okay. Now, in this figure that you're going to see here, excuse me. Okay, so here the converse of theorem 4.2 is not necessarily going to be true because it is possible for f prime of C to be equal to 0 at the point without a local maximum or local minimum value occurring there. Like in this case right here, this graph on the left, here we got y equal f of x. Here f prime of C is 0. The problem with that is that there is no local maximum or minimum at C. And it's also possible that f prime of C fails to exist with no local extreme values occurring at C. So here you can see on the right here that here f prime of C does not exist, but of course there's no local max or min at C. So therefore, critical points are considered to be candidates for local extreme points, but you must determine whether they actually correspond to local maxima or minima. Okay. Now let's look at example 4. And in this case here, we're going to find the critical points of any of the following function on the domain. That's part A. And then part B, we're going to use the graphing utility to determine whether each critical point corresponds to a local minimum, local maximum, or neither. So in this case, we got f of x equals to 4x squared minus 3x plus 1. And here I want to find those critical points. Well, to do that, you have to take the first derivative. Now I'll go ahead and rewrite the function f of x is equal to 4x squared minus 3x plus 1. So here you have to take the first derivative, or the derivative of that function. So f prime of x will be 4x squared. This derivative will be 8x minus the derivative of 3x is 3. The derivative of a constant is 0. So f prime of x will be 8x minus 3. And then next, you're going to set f prime of x to be equal to 0. And since f prime of x is equal to 8x minus 3, that 8x minus 3 will be set equal to 0. And then we're going to solve for x. So if I add 3 to both sides, that would mean 8x is equal to 3. Divide both sides by 8. X is equal to 3/8. So x is equal to 3/8 is going to be that critical value. Okay. I think in the homework, they just want the critical value. So that critical value would just be x is equal to 3/8. Now in part B, they want us to use the graphing utility to determine whether each critical point corresponds to a local minimum, local maximum, or neither. So this is where we use our graphing calculator to do this. Okay, I'll clear this out. And then for f of x equal to 4x squared minus 3x plus 1, that will go into y1. So I'm going to press y1, clear this equation. Y equal to, clear the equation out in y1 and type in 4, and then xt theta n for the x, and then the x squared minus 3 xt theta for the x plus 1. And I'm going to use the standard window like Zoom 6. Okay. And what I might want to do here is go ahead and do zoom. Let's say zoom in. So zoom 2. And then I'm going to press enter to get a better view of that graph. And pretty much if you look at it, that's the graph of a parabola. Okay. Because it is a quadratic function. All right. So that x equals 3/8. I'm assuming that's going to be this lowest point on the graph that you see here. That corresponds to a local minimum, okay? Because that's going to be the lowest point before it starts going back upward. So x is equal to 3/8 will correspond to a local minimum. X equals 3/8 corresponds to a local minimum. All right, now let's look at example 5. So we're going to up the type of graph, a function that we have here. So here I want to use the function below to answer parts A and B. Here we got f of x is equal to x cubed over 3 minus 25x, and we're on the interval -8 to 8. Here I want to find the critical points of the function on that given interval, and then we want to use the graphing utility to determine whether each critical point corresponds to a local maximum, local minimum, or neither. And in the homework, you'll be able to choose a graph. And if necessary, fill in the answer box to complete your choice. All right, so now in part A, we got f of x is equal to, I'm going to write that x cubed over 3 as 1/3 x cubed minus 25x. So here I'm going to do f prime of x, which will be 1/3. The derivative of x cubed will be 3x squared minus the derivative of 25x will be 25. And notice that these 3's are going to divide out. Here you'll be left with f prime of x being equal to x squared minus 25. And then we let f prime of x equal to 0 to find our critical points. And f prime of x is that x squared minus 25 equal to 0. And then to solve for x, we're going to add 25 to both sides. So that means I have x squared is equal to 25. And then to solve for x, I need to take the square root on both sides and include that plus or minus symbol. So that means x is equal to plus or minus 5. So these are my critical values here. That x is equal to 5 and x is equal to -5. Those two x values represent critical values. And then part B is to use a graphing utility to determine whether each critical point corresponds to a local minimum or local maximum, or neither. So I'm going to put the original function in the graphing calculator. So here I'm going to go to y equal 2 and clear this equation out. And then I'm going to type in the x for the x, and then the hat key, and then the exponent of 3 for x cubed. Use my right arrow key and then do divide by 3 minus 25, and then x. All right, now I'm going to press the window key because notice the interval is from -8 to 8. So x min will be -8, x max will be 8. I'm going to let the x scale be 1. Y min, I'm going to go out on a limb here and do -10 for the y min, and the y max will be 10. Y scale will be 1. Then do the graph. Okay. All right. Let me change the window for the y max. I'm going to do -100 to 100. And then the y scale will be 10. There we go. So now you see what that graph looks like. And in this case here, I know -5 will have to be to the left. So this -1, -2, -3, -4, -5. It's right here. That's going to be the highest point. At -5, that corresponds to a local maximum because that's the highest point there on that interval from -8 to 8. Where +5, here's 1, 2, 3, 4, 5, that has to be a point that's the lowest on the graph. So at x is equal to -5, it corresponds to a local maximum. And at x is equal to 5, it's going to correspond to a local minimum. Okay. So again, you can see where -5 is. That's the highest point. So that's a local maximum. And here's +5 here. That corresponds to the local minimum. Okay. All right, example 6. Say you had a graph like this. Let's say we had the function f of x equal to 2x cubed plus 5 halves x squared minus 6x. And the interval we're dealing with is from -2 to 2. And again, I'm going to find the critical points of the function on that given interval and use the graphing utility to determine whether each critical point corresponds to a local maximum, local minimum, or neither. All right, so in this case here, we're going to do part A. So here's our function f of x is equal to 2x cubed plus 5 halves x squared minus 6x. And now let's take that derivative. So f prime of x would be this. The derivative of 2x cubed is 6x squared plus the derivative of, well, we bring down the 5 halves, but the derivative of x squared would be 2x. But if I do 2 times 5 over 2, that's going to be 5 times x minus the derivative of 6x is 6. Okay, so that's our derivative. We set that derivative to be equal to 0, so that means 6x squared plus 5x minus 6 is equal to 0. And trust me when I tell you this, we can factor this into 2 binomials here. The 6x squared, I'm going to use 2x and 3x. And here I'm using trial and error. And then the factors are -6, I'm going to use 3 and 2. So I have to make one negative and the other one be positive. So that means the 3 has to be plus and the 2 has to be minus. And I have to do that in a way so that the outer, which is -4x, and the inner, which is 9x, adds up to 5x as the middle term. So now we're going to set each binomial factor equal to 0 and solve the x. So I'm going to have 2x plus 3 equal to 0, and 3x minus 2 is equal to 0. And then for 2x plus 3 is equal to 0. If I subtract 3, you'll get 2x is equal to -3. Divide by 2, you'll get x is equal to -3 halves. And then for 3x minus 2 is equal to 0. If I add 2 to both sides, you'll get 3x is equal to 2. Divide by 3, you'll get x is equal to 2/3. So these are my 2 critical values here. They're going to be x is equal to -3 halves, and the other one will be x is equal to 2/3. Okay, so now we're going to use a graphing calculator to determine whether each critical point corresponds to a local maximum or local minimum or neither. All right, in this case, I'm going to go to y equal to, clear this equation out. For 2x cubed, that'll be 2, x t theta for the x. Press the hat key and then type in 3. Use the right arrow key to guide the exponential part, and then plus. Let me put 5 halves in parentheses. So I'm going to do left parentheses 5 divided by 2, close parentheses, and then get the x and then square it, minus 6, and get the x. Then I'm going to go to my window. Let's see here that x min is from -2 to 2. So my x min will be -2. X max will be 2. I'll let the x scale be 1. And I'll leave y min -100 and y max +100 with a y scale of 10. Let's see what happens here when I graph this. Okay. Sometimes you gotta play around with your graphs here. So if I do -50 to 50 in increments of 10, okay, -50. Okay, I might need to just zoom in a bit. Okay, that will look that's a little bit better. We'll zoom in some more. Okay. Okay, guess that's going to be the best we can do here. All right, so for -3/2, which is like -1.5, that's over here somewhere. This corresponds to a local maximum because that's the highest point on this graph. Now for 2/3, which is about right here, is a little bit less than 1, but that corresponds to a local minimum because that's the lowest point on the graph at 2/3. So that means here, x is equal to -3/2 will correspond to a local maximum. Now for the x is equal to 2/3, it's going to correspond to a local minimum. Okay. So pretty much you have to use the graphing calculator to kind of get an idea of how that's done. To identify which one is a local maximum, which one's a local minimum, or neither. All right, here's one more of these. Let's say I want to find the critical points for the following function on the domain and use the graphing utility to determine whether each critical point corresponds to a local maximum, local minimum, or neither. And here I got f of x is equal to 1/x minus ln of x. All right, by looking at this particular function, I can identify the domain. I know for the 1/x, it can't be 0 because I know division by 0 is undefined. Also, look at ln of x. That function is restricted on this interval, 0 to infinity. I cannot take the natural log of a negative number, and I cannot take the natural log of 0. So the domain in this case is going to be from 0 to infinity, not including 0. Now let's go ahead and take the derivative of this function so that we can find our critical values here. I'm going to rewrite the 1/x in exponential form using negative exponents. And that's x to the -1 minus ln of x. Now let's take the derivative here. F prime of x will be this. For the derivative of x to the -1, I have to bring the exponent down. That's the -1. Copy over the x to the 1 less power. So -1 minus 1 will be -2. And then minus the derivative of the natural log of x will always be 1/x. Now let's write this using positive exponents here. So here I got -1 in the numerator. That x to the -2 will go down in the denominator as x to the +2 minus 1/x. Now, if I write this by using the LCD of x squared and x, I'd use the x with the largest exponent. That LCD would be x squared. Now, if I want this to be x squared, I need to multiply the numerator and the denominator by x. So here I'm going to have the -1/x squared minus 1 times x will be x over x times x will be x squared. And since now the denominators are the same, I can write the negative 1 minus x all over x squared. So this is what f prime of x is going to be. Now, to find your critical values, we know that at 0, here f prime of x does not exist here when x is equal to 0. Okay, so what we have to do there is set the numerator, which is negative 1 minus x, to be equal to 0, and set your denominator x squared to be equal to 0. Okay, so when we solve for x here, if I move this x over to the other side by adding x to both sides, I'm going to have negative 1 is equal to x. And then for the x squared equal to 0, if I take the square root on both sides, we get x is equal to 0. We got a problem here. At negative 1, that's not in the domain. And at 0, that 2 is not in that domain, 0 to infinity. So we can scratch these out. Because for negative 1, I cannot take the log of a natural log of a negative number. And for 0, I will get a 0 in the denominator, and I cannot take the natural log of 0. So we have to eliminate both of these candidates for critical values here. So in this case, this function f of x has no critical values. Okay, so that's part A. Now, if we were to graph part B, well, for part B, if we were to do the graph like this, let's go to y equal 2, clear this out. And I'm putting 1 divided by x in parentheses, and then minus the ln key, and then get the x. And let me do zoom 6 for the standard window. So as you can see here, there's not going to be a local maximum or a local minimum from 0 to infinity. Okay. There is no absolute highest x value, nor is there a lowest y value here. So in this case here, you will have neither a local maximum nor a local minimum. Okay. Okay. All right, next we'll look at locating absolute maxima and minima. Okay. Locating absolute maxima and minima. Now, Theorem 4.1 that we just got through talking about at the beginning, that guarantees the existence of absolute extreme values of a continuous function on a closed interval a, b, but it does not say where these values are located. Two observations lead to a procedure for locating absolute extreme values. One of them is an absolute extreme value in the interior of the interval is also a local extreme value. And we know that local extreme values occur at the critical points of f. And absolute extreme values may also occur at the endpoints of the interval of interest. So these two facts suggest the following procedure for locating the absolute extreme values of a continuous function on a closed interval. So here's the procedure for locating absolute maximum and minimum values. we want to assume that the function f is continuous on the closed interval AB. Number one, you want to locate your critical values or critical points, which is C, in the open interval AB, where f prime of C is equal to 0, or f prime of C does not exist. These points are candidates for absolute maxima and minima. And then number two, you want to evaluate f at the critical points and at the endpoints of the closed interval AB. Then number three, you're going to choose the largest and smallest values of f from step number two for the absolute maximum and minimum values, respectively. Okay. Now you want to note that the preceding procedure box does not address the case in which f is continuous on the open interval. If the interval of interest is an open interval, then absolute extreme values, if they exist, occur at interior points. All right, so now let's look at this example number 8 on your handout and see how we will be able to do this one. All right, here we're going to use the given information and the given interval below to answer parts A through C. Here we got f of x is equal to x squared minus 9 on the interval -3 to 4. And here I want to find the critical points of f on the given interval. And in this case here, we want to determine the absolute extreme values of f on the given interval when they exist, and then use graphing utility to confirm your conclusions. All right, so let's start by finding our critical points. Our function is f of x is equal to x squared minus 9. So now let's find the derivative of that. So f prime of x would be equal to the derivative of x squared minus 9 is simply going to be 2x. And then we set that f of x to be equal to 0. So that means 2x is equal to 0. And then divide by 2, you'll get x is equal to 0. So we know our critical point is going to be at x is equal to 0. So now in part B, we're going to determine the absolute extreme values of f on the given interval when they exist. So we have to use that x equals 0 in our original function, f of x is equal to x squared minus 9. And also we're going to evaluate f of -3. That's our endpoint. And the other endpoint is 4. So we're going to evaluate f of 4. And that will help us determine our absolute maximum and absolute minimum. So at x is equal to 0, starting off with that, we substitute the x with 0 in this original function that we started off with, x squared minus 9. So x is 0, so 0 squared minus 9. 0 squared is 0, minus 9 would be -9. And now for f of -3, substitute the x with -3. That'd be -3 squared minus 9. -3 squared is -3 times -3, which is positive 9. And 9 minus 9 is 0. And then for f of 4, substitute the x with 4, so it'll be 4 squared minus 9. 4 squared is 16. 16 minus 9 is 7. So from these values, we're going to find out what our absolute maximum and minimum are, starting with the absolute maximum. So the highest value that we got from these three is 7. So the absolute maximum is 7, and that occurred when x is equal to 4, because we replace the x with 4 to get 7. So the ordered pair for our absolute maximum would be 4, 7. And then our absolute minimum that's the smallest of the three y values that we got here. In this case, that's 0. And that occurred when x is equal to -3. No, I'm sorry. It's not 0. It's -9. -9. And it occurred when x is equal to 0. Okay, so the absolute minimum is -9 when x was equal to 0. And the ordered pair for that would be 0, -9. Okay. Okay, now example 9. Here we're going to use a given function and the given interval to complete parts A through C. Oh, let me go back to part C. Example 8, because I forgot to do part C here. And we can use the graphing calculator to get our conclusions here. So go to y equal to the previous equation out and type in x and then square minus 9. The window will be from -3 to 4 in increments of 1, and then graph. Okay. So pretty much at 4, you'll see where it reaches 7. Okay. And you can verify that by doing this second table. So you can see at -4, it's going to be at 7. And then when it's 0, it's going to be -9. And again, there's a graph right there, -9. That's the absolute maximum on that minimum. And here, that's the absolute maximum right there at 4. All right, now example 9. Here I want to use a given function and a given interval to complete parts A through C. Okay, so it's pretty much the same thing as example 8. But my function here is f of x is equal to x minus 1 raised to the 4/3 power. The interval is from -6 to 6. Okay, so let's find our critical point. So here we got f of x is equal to x minus 1 raised to the 4/3 power. Now let's take the derivative of that. So f prime of x is this. We bring the power down, which is your 4/3. Copy the x minus 1 over to the 1 less power. 4/3 minus 1, which is the same as 4/3 minus 3/3, which is 1/3. Now you can take the inside derivative of x minus 1, which will end up being 1. And now we take f prime of x, set that equal to 0. And f prime of x was the 4/3 times x minus 1 to the 1/3. That'll be set equal to 0. All right, now in this case here, to get rid of the 4/3, I need to multiply both sides by the reciprocal, which is in this case 3/4. Okay, so that 3/4 would be multiplied by all of this. That's equal to 0 times 3/4, because 3/4 is the reciprocal of 4/3. And what's going to happen here is that 3/4 times 4/3 ends up being 1 as a product. So you'll have x minus 1 to the 1/3 equaling to 0. Now, another way of writing x minus 1 to the 1/3 in radical form would be the cubed root of x minus 1 equaling to 0. And here I'm going to continue this on over here. The opposite of the cube root would be to take the cube on both sides. And that wipes out the radical. So I'll have x minus 1 is equal to 0. And to add 1 on both sides, you'll get x is equal to 1. So my critical point would be x is equal to 1. Okay. So now in part B, I want to determine my absolute extreme values of f on the given interval when they exist. So in this case here, I need to evaluate f of 1. That's my critical point. And then f of each endpoint, f of -6 and f of +6. And here I'm using the original function up here and replace each x with those values. So starting with f of 1, I'm gonna have this. X will be 1, so it'll be 1 minus 1 raised to the 4/3 power. Well, 1 minus 1 is 0. 0 to the 4/3 is 0. Now for x equal -6, here's one we'll have. X is -6 minus 1 raised to the 4/3. -6 minus 1 would be -7 to the 4/3. And here I'm going to use my graphing calculator to simplify -7 to the 4/3. So I'm going to put this in parentheses, -7, close parentheses, press the hat key, and then 4 divided by 3. And I can press enter from here. Now the 2 decimal places, this will be approximately 13.39. And now for f of f of 6, this will be 6 minus 1 to the 4/3. And 6 minus 1 is 5, and that's going to be raised to the 4/3. So using a calculator, 5, hat key, 4 divided by 3. To 2 decimal places, that's approximately 8.55. Okay. So that's what's going to help me identify the absolute maximum and absolute minimum. Let's start with the absolute maximum. That's going to be the highest of these 3 y values here, which is in this case 13.39. That's my absolute maximum. And that occurred when x was equal to, in this case, -6. And for the absolute minimum, that's the lowest of these 3, which was 0. And that occurred when x was equal to 1. Okay. Now you probably could write those as ordered pairs, like -6 and 13.39 for your absolute maximum, and then 1, 0 for your absolute minimum. And if you want to verify that on the graphing calculator, you can do this. Go to y equal 2. And then I'm going to do left parentheses, x minus 1, close parentheses, the hat key for your exponent, 4 divided by 3. Then I'm gonna go to my window. I'm gonna let X min be -6 and Y X max be 6. And then do the graph. So pretty much you can see what the absolute min is going to be at 1, 0. Now, if I change my window a bit, let's see. If I let that Y min be -20 to 20 in increments of 2, so pretty much you can see what's happening here. Because as you can see at -6, it's going to be 13.39. All right, and finally, example 10. The instructions are pretty much the same. Our function is f of x is equal to x to the 2/5. And it's on the interval from -9 to 9. All right, so let's first find the critical points on this given interval. So here, f of x is x to the 2/5. And if I want to take the derivative of that, which is, of course, f prime of x, that will be bring down the 2/5, copy over the x to the 1 less power. If I do 2/5 minus 1, and I'll do that on the calculator so you can see how I'm getting this. 2 divided by 5 minus 1, then press the math key, number 1 for fraction. It'll be -3/5. So I get 2/5 x to the -3/5. And if I write that using positive exponents, the 2 will be in the numerator, the 5 will be in the denominator. I'll bring x to the -3/5 in the denominator as x to the +3/5. So now f prime of x is in the form of a fraction, a rational function. So I need to set the numerator, which is 2 equal to 0, and 5x to the 3/5. That's the denominator equal to 0. Well, 2 equal to 0 is not true, so I can cross that out altogether. But 5x to the 3/5 equal to 0, if I divide both sides by 5, that means x to the 3/5 is equal to 0. And to get x by itself, the reciprocal of 3/5 will be 5/3. So I'm going to raise both sides of this equation to the 5/3 power. So that means x then will be equal to 0. So this x equals 0 is the critical value. And now we want to determine our absolute extreme values here. All right, so here's part B. We're going to substitute the x with 0 to find out what f of 0 is at the critical value. And then we got -9 to 9. So we want to evaluate f of -9 and f of +9. Well, in this case here, f of 0, we substitute the x with 0 in the original function that we started off with. So that means that's going to be 0 to the 2/5. And if you do this in the calculator, it's going to be 0 because the 5th root of 0 is 0, and 0 squared is 0. Now for -9, this will be -9 to the 2/5 power. And I'm going to use my calculator to determine my absolute maximum and absolute minimum. So -9 needs to be in the parentheses. Use your hat key for the exponent, 2 divided by 5. Let's say the 2 decimal places. This is approximately 2.41. And then for f of 9, that's going to be 9 to the 2/5. So 9, hat key, 2 divided by 5. That's also 2.41 as well. So as you can see here, at x equals 9 and x equals -9, I have an absolute maximum. And I'm going to use +9 to the 2/5. And that is when x is equal to 9 and x is equal to -9. And I say +9 to the 2/5 because even though this is negative, this 2 here is to an even power. So if you square something that's negative, that's going to be positive. So it'll be 9 to the 2/5 anyway. So at -9 and 9, my absolute maximum will be 9 to the 2/5 power. And of course, 0 will have to be the absolute minimum. And that is when x is equal to 0. All right. Now let's graph this to verify or confirm our conclusions here. Go to y equal to, get the x, and then the hat key, 2 divided by 5. Then I'm going to go to my window and say -9 for x min and y for x max. And if you want to see this a little bit better, let me change my window and do from -5 to 5. And sometimes you just got to play around with this just to get a better view of this. So you can pretty much see where your relative maximums are, or maxima, and your relative min is at that point. Okay. All right, so that does conclude this video, section 4.1, dealing with maxima and minima. Feel free to contact me if you have any questions or comments regarding anything that's presented in this video or any of the homework problems in my math lab.